So a baseline is our way of almost saving ourselves work. Because if we now see that we are getting what we expect for our baseline, we can kind of just check off that part of the process and say, okay, we don't have to go diving into exactly how is this thing working and exactly what is Java doing, and let's build the interpreter from scratch and step through it, or any of that. Like, we don't have to do all that work if we can just see that our baseline carried through, because then we know for our purposes, everything's working well enough.
Hi folks, and welcome to a new episode of Marco Code, and the second episode in solving Java's 1 billion row challenge. Just a quick recap of what we did last time. Essentially, we are still at the, let's read in a file stage. And I showed Casey a bit of code with a map byte buffer, which is basically a memory map file in Java. We had a discussion around that, and we ended with some homework. We said, well, scratch the Java code for now. Let us establish a baseline. The baseline being, hey, what is the speed of my SSD drive? How fast can we actually read in, the file into my Java program and process it later on? And what is then also the specs of the underlying machine where they actually run the challenge? So we're going to focus this episode on establishing the baseline. There are a ton of things which I learned during the process. I felt punked pretty much during the process. And then I noticed it was the challenge, it was me partially, but we're going to figure these things out. So Casey, let's bring you back on.
Hello, Marco. It's good to be back on.
It is really good to see you. So
you said you felt punked. Was the challenge, you felt like the challenge organizer was punking? What happened?
Yeah,
I don't understand.
I felt like the challenge organizer was punking us, but I'll show you in a second what I actually, it was my own stupidity in the end. I mean, I can't complain. I can't really complain. So let me walk you through what I did. Because I wrote down the homework like a good old student does. So what's the speed of my SSD? And I just started with that. And I had a look around. I'm running on a Mac Mini here. And I had a look around online and said, hey, what's the speed of my Mac Mini? Couldn't really, of my SSD drive. Couldn't really find anything. Then, nothing where I said, this is really hard data. Then I looked for commands, essentially, which I could execute, which would tell me at least what specific model my SSD has. I got the model. Again, I browsed online. I found conflicting data from 2 gigabytes to 6 gigabytes a second. And the websites felt kind of dodgy. And I wasn't really sure if that is kind of, what I was looking for. And at that stage, I thought, well, I'm going to jump straight ahead to the last part of the homework where it says, well, what's the underlying specs where they run the challenge? And this is where I felt punked.
Okay.
I'll tell you why. So you have to imagine, I had a look at that challenge like 1.5 years ago, and then, I did minimal preparation for this series.
Oh, programs are run from a Ramdisk.
Oh, yeah, exactly.
Very interesting, Marco.
So what happened is, I had a look at this line. So I looked at evaluation results, and I said, well, it's a Hetzner machine, a server, 32 core, 128 gigabytes of RAM, and then I stopped reading. So I did. I stopped reading, and I thought, how funny is that they don't even mention, the SSD speed, and how can they even publish results, not mentioning these SSD speeds. And what I did is I went to the Hetzner website. I tried to find the server. I saw that they actually don't really sell that specific server model anymore.
Okay.
And then I did the next best thing. I had a look at the closest model number. I actually opened and tried to have a look at, hey, what is the SSD speed? What is the speed these SSDs have?
Gotcha.
I found out that they don't really publish them. So what you can see here is you just see it's an SSD drive, NVMe, but speed-wise, I didn't really know.
Right. They probably have different ones. They might even use different ones depending on what batch they were installing or whatever, right? Yeah.
Exactly. So I opened up a ticket with Hetzner and said, hey, dudes, what is the specific hard drives you basically put into these machines? And they said, well, we have different ones, but we can give you all these, the models. So I got the models. I looked
oh, my God, Mario, I feel so bad.
It's perfect. It's perfect. And we need to show people the process because, you just look at these pages, you have these big numbers, you have no idea, what that server can actually do.
Yeah.
And I wanted to find out. So I got the model numbers, the model types and whatnot, had a look at their speeds. When you look at the manufacturer website, you see like 6 to 7 gigabytes a second, that sort of stuff. And then Something else happened. Because again, it's a topic I don't worry about too much, but PCI Express, different versions, PCIe 3, 4, 5. What I learned, and you need to tell us a bit more about that. I learned essentially when you look at PCI Express, your SSD drive has a couple of data lanes, which they shoot data through. I learned that with PCI Express version 3, to make it very simple, each data lane has roughly 1 gigabyte a second. There's usually 4 lanes, which makes it theoretically the throughput for these types of hard drives is actually 4 gigabytes. And is that true, kind of?
I'm not going to remember any of that stuff off the top of my head, but yes. I mean, basically, the situation that you get with these sorts of things is the CPU itself has some number of PCIe data lane support, right? Like, so there's a maximum that can be connected. And then the motherboard connects those lanes to various slots, and each sort of PCIe version has a certain maximum number for the slot. And so at the end of the day, you have to look at so many things. You have to be like, okay, what is the chip in the motherboard? And then like which slot is the SSD in? Because a lot of ones, they have like a slot that has more lanes than another slot, and all these other sorts of things. So, but yeah, you're doing everything right. I wouldn't be able to correct you off the top of my head though, because I don't remember like all of the specific, right?
Right.
Yeah, continue.
And to make it very simple for people, so PCI 3, let's say 4 gigabytes a second, theoretical throughput. So not maximum throughput, because these drives, they never go at the maximum throughput. PCI 4, just double it. So let's say roughly 8 gigabytes a second. PCI 5, PCI Express 5, roughly double it again. So we're talking 15 gigabytes a second or something along these lines. And then I thought, well, how funny is that? They're posting results where they say it takes you 1 second or less than a second, to process the entire file. And I thought, hold on a second, these servers, PCI 4, whatever, let's say 8 gigabytes a second, it takes you even 2 seconds to read in the file. There's no way they can actually process it in less than a second. And so I was a bit stuck, and I thought, they must be jokesters or whatever. And then I found out, well, I'm the jokester, because, yeah.
Except you're not really the jokester, because I feel like that was a really, like, valuable exercise to do, because now we kind of know, like, the challenge is sort of fake. Like, we took disk I/O out of it, which, I mean, it is worth thinking about when you are working on performance, because depending on the situation, you may be in a case where you're reading files that were recently written and they're likely to be in the cache or things like that. But it's like, okay, why are we reading a file? If we're doing memory to memory, why wasn't this just in shared memory or something? Like what is the actual real world scenario where we're pretending this happened? It's kind of weird, right? So it feels a little artificial, and, at that point, even though it's an artificial exercise, it's like you want the exercise to kind of mirror something that you're likely to be doing. I don't know, but maybe, you could say, all right, people are running Ramdisks for performance sometimes, so it's kind of like that. Maybe we'll say, I don't know. But yeah, I think it was a great exercise, because all the things you just said are things that are great to know. Yep. A little bit weird that they didn't, actually have us do some SSD stuff, but that's fine. Now we know, and we know that our baseline is basically, it's going to be a little hard for us to measure, because we don't really know specifically what the RAM disk performance will be on this particular machine, but we do know that we're targeting something more like memory speed, which is much, much faster than an SSD can read in a typical configuration.
And to be honest, what I thought, I want to finish off this exercise, at least on my machine, just with the file reading and the file loading, because as you said, in the real world, there's never ever going to be a workload where you just have magically a warmed up RAM disk lying around, and then you can just process whatever's on that RAM disk. So I think the whole file stuff, and this is what we're going to be talking about the rest in this episode, is hugely exciting. And by the way, I asked a couple of ex-colleagues, old Java, workers, how long would you reckon it takes to read in a 15 gigabyte file?
Yeah.
And I got answers, from, I don't know, minutes to whatever, but it's just 2 seconds. Let's say it's just seconds. And it's so important for people to understand. it's massive speed. I mean, it's just it takes you 2 seconds, which for this challenge might be 2 seconds, but in the real world, it's a lot of data you can actually read in a second.
Well, and I think just to underscore why I don't think you were, I feel like the challengers were, the challenge organizer, whatever you want to call them, we're pulling a little bit of fast one there. It's like, just to let you know, when we were talking last time, in my head, when you showed those numbers, it was like 1 point something seconds or whatever. In my head, I actually thought that sounds faster than possible. That was literally what I thought in my head. I was like, I don't think you can pull off the SSD at that speed for this size of a file. That was my thought. So my intuition was also that there's something funny going on here. So the organizers kind of did pull a little bit of a fast one on both of us, and I'm glad we have now seen that that verbiage there that let us know, okay, we've got a RAM disk. Now hitting something like 1.x seconds seems very doable, right? Whereas before I was like, I don't know how we're getting this data in that amount of time. Like, but yeah. All right, so great. We've got some really good information here. Great. So what are we doing today then, Marco? Where are we going?
The story continues because we're actually not done yet with the disk speed, because I then got back and I wanted to know, what is the speed of my SSD? I want to have real proper numbers.
Okay.
Real proper numbers. And I thought about, hey, how do I actually benchmark my disk speed? And there's a ton of command line tools. There's a ton of stuff out there, and 20 million options. And I thought, well, fuck it. What I'm just going to do is I'm going to use a good old tool which existed for 50 years. I'm just going to use DD here, where I'm going to take my measurements TXT file. I'm just going to pipe it into dev null, which essentially is like reading in the file, and hopefully no overhead for letting the kernel, put it to dev null or discarding essentially all the input. And I said, well, I'm just going to run that with block size, a parameter, which I'm going to ask you in a second, just 1 megabyte, because it sounded like, why not? Why not 1? Why not 10? I didn't know. And I just ran it. And I got, roughly 2 seconds out of that. DD gives you just the number of bytes a second. What I find is with these sort of numbers, to make it really simple, kilobytes, megabytes, we have 6,500 megabytes roughly, even though it's not entirely correct. So 6.5 gigabytes a second, which, is a fairly nice speed, I felt, from my hard drive.
Well, I guess I'm not sure what exactly that's going to do, though, because the measurements.txt file is that the list of cities?
Yeah, exactly. Yeah.
So again, the problem that you get with something like this is I don't know what is DD guaranteed to raw read as opposed to going through the file cache. I don't know the answer to that question.
Well, here we go. So I thought, if we run it again.
Yeah.
If we run it again, actually, that was now a bit slow, but it should actually be, exactly. So you see 1 second.
Okay.
If you rerun it. And I thought, well, then what we need to do is, because we said, hey, roll the file system cache.
Yeah.
Let's delete the file system cache for everything we do. Let's just purge the file system cache, rerun it. And then we get a cold number,
nice. Okay.
Which hopefully is the number we're going to be working with.
Okay, so I think that's important for viewers to understand, right? You see why I asked that question, because you do have the file system in the background. The file system, or I shouldn't say the file system, but the operating system, which is, implementing this file system, it's always doing some work to try to give you faster speeds by keeping things cached in memory, right? And by the way, this is also something that you should think about when you're dealing with spinning platter drives as well, or sometimes even SSDs. It really depends on the circumstance, because there's really, you can almost think of it as there being sort of 3 possible rates that you're going to get. One is if you have to read it off of the drive, like we're getting it off of whatever the real storage is. Another speed, and of course that's gated by how fast it can read, and then like you said, how many PCIe lanes are coming through, right? So that whole process, and the overhead of the kernel to read it, everything that's going through the whole thing. Then the next speed is if this drive has a cache on it. Because, for example, spinning platter drives, which have a much harder time doing things like seeks and may have a much slower sustained read speeds, things like that, they will often have like RAM sitting on them that caches things on the drive side that then delivers you like burst reads and writes and things like that, especially for writes, for example, which, would be slow. It'll like store up stuff, so it appears to be writing really fast at first, things like that. So there's that. Then finally, there's the speed of if the OS itself has cached this thing. So it told you the write was done or it told you the read was done, but really it's just the operating system has buffered it and it's dealing with it in some other way, right? So you do always have to be aware of that there's these different speeds. And when you actually want to do it, like what you did with that purge is a really good idea. That won't really help you with if there's something happening on the drive side, but it will at least let you know, okay, if we get the operating system out of the way, what am I actually getting from the drive in this scenario? So yeah. Right. Looks great.
And at the end, as a rule of thumb, I guess, what I'm most interested in, at the beginning at least, is, what's the worst case scenario kind of? What is, if I have a cold start kind of, what is the worst speed I will get? And I don't want to immediately go to, hey, the file has been cached. And I don't even know, by the way, is there a way for me to really dig deep into what the operating system does, what parts have been cached and how, and could I kind of visualize that somehow?
So first of all, I'm not very useful on a Mac with stuff because I normally am on Windows. And so my knowledge of what you might be able to get on Mac is unfortunately much more limited than it would normally be. But even on Windows, I've never really done a thing that interrogates what files are specific, build me a map right now of which chunks of which files have been cached, right? I've never actually tried something like that. Mm-hmm. You can sometimes use operating system metrics. Operating systems often have a series of metrics that you can query, and I don't know which ones are available on Mac, but on PC, for example, you can load up perfmon or use event tracing for Windows, and you can actually typically get things like if you want to know whether there was a hard I/O operation, like an I/O operation that actually went out to the drive, as opposed to a soft I/O operation, which is one that the OS just kind of handled it and it never actually went out to a piece of hardware. You can get that kind of information, which is usually good enough because in most cases you don't need to know specifically the topology of what was cached. You usually just want to know how much caching behavior was happening in this run, and that you can get. And so Mac might have similar performance counters to that, but I don't know if that makes sense. So that might be, if you want to put that, if you're really curious about that, you could put that on something to look at before whenever our next stream is. You could try to see. If you wanted to do that investigation before next time as well, I don't know if it's appropriate or what stuff you want to work on, but one thing you could do is take a look at what is available for Mac OS level performance counters. Mm-hmm. Do they have something like that? Can you measure it? Now, that's not going to be that relevant for this challenge because we now know that we're working out of a RAM disk, so we're kind of taking that out of the equation. But if the goal of this series is just kind of to generally talk about performance and look at things, that would certainly be a great resource for your viewers. So if you're in the mood to look at it, we could certainly just slot in an episode where you and I talk about that as, at some point, whenever, right?
Yeah. Got it. I have one more question, though. Mm-hmm. So, as I said before, you have the block size parameter where you can just say, block size 1 megabyte. And as it happens, there are many operations where, you have to specify some sort of a block size when reading in files in Java, and there's some defaults. You look at the defaults, and you think, it's 8,192 bytes or whatever, and you're wondering, what does that number actually mean? Why should I take that number, not a different number? Why shouldn't I don't know. What is it?
I understand. So there are many reasons why block sizes are involved in performance-sensitive operations, if this makes sense. Mm-hmm. So the first way it comes into play in this is because specifically with disks, there are actually block sizes. Meaning disks themselves often have some kind of a sector size or things like this, depending on the type of disk that you're talking about, right? So at bottom, there may be an optimal size to ask the disk for itself. Now, why does that matter? Well, if you think about what has to happen, when you do a read of some kind, you're asking for something that will hopefully align with that block size. If you don't, then the operating system has to reassemble whatever the block is that you asked for out of multiple blocks, right? Because it'll straddle, if that makes sense. So the optimal way to read, which is hard when you're talking about files, because files don't necessarily start aligned on a sector size. You know, they may, or the operating system may try to do that, blah, 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 right? But the optimal thing you can do when asking for data is to ask for something where you doesn't have to be reassembled, where it could just be passed through directly, right? So some multiple of the underlying block size will always be like the least amount of work that anyone has to do, because they won't have to like read an extra block. Like the worst case I might say is like, suppose you only wanted to read 1 byte larger than the like block size of the drive. Well, now you're going to have to read 2 blocks off of the drive, or sector size, I should say, or something like that, right? You have to read 2 of them, and then you throw away most of that other read, right? Some of this, you can start to see now as I'm saying this, some of this explains why file caching was so important, like back in the day when you had much slower drives and these sector sizes were more important and things like that. Because it's like, now you can see if I was reading through a file, you would never want to throw away that block read because the person's very likely to ask for it again soon, right? And we don't want to go reread the block, right? So file caching became a very natural thing to do because you were like, oh, as I'm reading around and I'm asking, it was like the person reading the file probably doesn't know what the block sizes are or where these things were on the disk. So I'm going to cache the blocks as I read them in so that when people are doing these reads, they come out, right? So there's this whole machinery working down there that we don't think about, but it's all predicated on that. So that's one place where you think about chunk sizes. Move up a level to us, we're the one asking the operating system. Chunk sizes become important here because there are also many different types of like caching or overhead employed. When you ask the operating system to do something, there is an inherent overhead in that entire transition. I have to like go to the like if you imagine what happens in an immediate call, like something where I'm literally blocking on the operating system. So I'm doing like read and don't return until you have finished reading. So we're not talking about like an IO ring or some kind of asynchronous IO, but we're doing a read right now. When I do that, my program is literally going to block. It will wait until the operating system has provisioned that into the memory of this process somehow. Now that whole thing, that round trip, we have to change from like a low privilege level, right, where our code is running in the CPU, to a high privilege level, which is where the kernel is running. In Windows, we call this ring 3 and ring 0. You have the same sort of things on ARM processors, but they're not called the same things. Again, I'm much less knowledgeable about Mac, so I try not to use precise terms there because I don't want to mislead anyone. But the same principle is happening. You have privilege escalation, but it's not called ring 3 on ARM. So anyway, you're going down to the most privileged thing where you can do anything you want, the kernel, right? It's then going to go, okay, I have to do this read for this person. Let me kick that off. Let's wait. We're just going to wait till it's done. Maybe it's in the cache, maybe it's not. If it's not, it's going to take a long time. It's going to go all the way out to the drive and come back, right? Blah, blah, blah. So what you see there is if I do all that and I'm just asking for 8K. Now, again, some people might think, oh, is 8K a lot? I don't know. Like, it's like, no, 8K is minuscule, right? A modern CPU can blast through copying like 8K in a blink of an eye, right? That fits in your L1 cache. It's so tiny. So all of that work to go through and do the sort of operation itself dwarfs the 8K actual, like, chunk you were asking for.
Right.
So the reason we start to care about chunk sizes at that level, because we're not raw reading, we haven't guaranteed they're aligned to the file. So like some of those things I've talked before, we don't really care about those. Why do we still care about the chunk size? For this reason. We want that chunk size to be big enough that we don't have a problem with, our overhead dwarfing our actual operation. At the same time, we may not want it to be so huge that it doesn't fit in the OS's L2 cache or L3 cache. On Mac, it'll be L2. That's the last level cache on most M-series chips. As far as I know, there's no L3 caches on M-series chips. But like on an Intel or x64 chips, it'd be L3. But anyway, your last level cache, we could talk about this at some point, cache that's shared by all the cores. We want it to stay in there. We don't want it to go out to main memory if we can avoid it, because if the operating system did have to pull it from a drive, we'd like it to stay hot in that L3 where we're getting a lot more bandwidth than if it has to go out to main memory and then we pull it back from the main memory, right? So we're picking that chunk size to be something nice that the operating system could transfer for us. Again, all this goes out the window potentially when we're talking about a RAM disk, because now we're thinking a little bit differently, but all the same things I said still apply. There still is the overhead. There's still a question about how do we want it to be cached and things like this. So does that all make reasonable sense?
It does make sense. It does make sense. It's a ton of background knowledge. Thank you for that. Let's get back to Java a tiny bit because, we've seen that, let's say DD tells us, I mean, it should take us roughly 2.1 seconds to read in the file, right? Yes. On a cold disk.
Yep.
And when I look at the homework, it says, well, what's the fastest to get it to read in Java? Yeah. So what I did is I created a new file, which is surprisingly called blah3. And in blah3, it's a very basic file. What we do is, what I did is, I did use every, let's say, API that you can use in Java, roughly, to read in a file or to read in bytes. And I made sure that, I ran sudo purge before every file read. So that we can actually, get proper results. And just for the viewers out there, there is just a couple of ways in Java to read in files. One you'll see is having a buffered input stream. Many people have seen these lines of codes in projects where you create a new file input stream, wrap it in a buffer. Again, you apply a magic byte size that people never know what kind of number to put there, or just use the defaults. Usually nowadays you'll find it wrapped in convenience functions with all the defaults being set for you. But again, that is, from Java 1 in 1996. I actually had to look up these years when they introduced the API. Then we have the Java's new I/O, which was introduced in Java 1.4. The funny thing is when you hear new I/O, 2002. I mean, it's
23 years ago. Yeah,
23 years ago. So that's also in quite a while. The map byte buffer that I showed you last time, where I said, hey, it had kind of a 2 gigabyte limit. Was also introduced in 2002, and we had a viewer sent me an email, Ludovic, which I did some stuff a while ago, and he mentioned that in 2002 when they did it, they went for int pointers, so to speak, or int indices, because I think at that time there was no 64-bit JVM that existed. There was no real 64-bit processor, whatever. Yeah. So it's just historical reasons why they had that limitation.
Yep.
And then, last but not least, there is an update to that API, to map byte buffer, with an API which came out last year, which is pretty new, I'd say, so March 24.
That's the real new I/O. Yeah,
that's the real new I/O. And there have been different new I/O versions and updates, obviously, in between. But anyway, you now can use a map byte buffer with any size file. At the end of the day, what I did is I just had these three methods here. I commented out buffered input stream because it took too long, or it takes too long to actually show you how long it takes to read in the file.
Oh my God.
You can look at, I mean, it takes you 50 seconds or whatever that is.
Wow.
So it took way too long.
Okay.
And maybe,
all right.
Right. Yeah. And then I just said, well, yeah, we're just going to run it, and we're just going to show people how long that stuff runs on my machine. So we're running through this. You can see we did a sudo purge. We're using the file channel method, which is the new I/O, and it took me 2,146 milliseconds.
That's really nicely in line with what you got from DD, isn't it?
It is pretty nicely in line with what I got from. Let me just double check with DD. Yeah, I mean it's it's pretty much the same thing, kind of.
Yep.
And let me just quickly double check. Then my map byte buffer, the version where I had to actually, the 2 gigabyte version, where I had to create multiple map byte buffers then, and just loop through them. 21 seconds, it kind of looks a bit off. So maybe I did something wrong, but who knows? And the map byte buffer, where I don't have to play with the 2 gigabyte size, took us 4.2 seconds.
Which seems in line with what you were showing me last week.
Yeah, I think so. Yes. Yeah.
Or last time, I should say.
Yeah, last time. Yeah.
So if I could comment on this a little bit.
Yeah.
2 things. One, this is great. I love what you did here, right? This is exactly what we want to do. It gets us started down the exploration path of let's see what all these things do, and we can interrogate any one of them further if we decide we care about why it's getting what it's getting, right? So, for example, I don't think we necessarily care that much in this series, but if I was just, if I'm just sitting around and I'm supposed to be doing performance investigations for Java, I would immediately dive into what's going on with that buffered input. Why is it taking 50 seconds? Let's go figure out why, and let's post some issues if it's not us. Like, if it's not some mistake we made, let's post some issues because that's a disaster, right? So anyway, this is great. It gets us exactly what we need. And a couple things. Here is why I said right off the bat, let's establish a baseline, right? Just from you having somebody external to compare to, some idea about what the speed should be, a separate benchmark that we can run and get something. We saw a reasonable value come out of that benchmark, and now we're seeing us get the same thing as the benchmark. Why is this important? Well, if you haven't noticed from many of the asides that I give you, when you ask me a question, you say, what about this thing? And I go on for 10 minutes explaining all of the things going on. The machinery is very complicated, and it isn't actually that hard to keep in your head what all the possible parts are. But it does take oftentimes quite some time to investigate if they're all working optimally and things like that. So a baseline is our way of almost saving ourselves work. Because if we now see that we are getting what we expect for our baseline, we can kind of just check off that part of the process and say, okay, we don't have to go diving into exactly how is this thing working and exactly what is Java doing, and let's build the interpreter from scratch and step through it, or any of like, we don't have to do all that work if we can just see that our baseline carried through, because then we know for our purposes, everything's working well enough. And that's usually what we care about in performance. We want to see that we didn't lose much. If we lost a few percent, that's fine these days, right? Unless we're talking about optimizing the crap out of a data center because we're at Google and any byte we save is multiplied by 100,000 or whatever, right?
Right.
Then this is good. We're like 2146 milliseconds. That's right in line with our thing. I think we're good. We could move on, right? We see that second number or that third number and we're like, even that third number, that's 2x off. That feels like we're giving up too much. We'd investigate it. So does that make sense? What I'm saying there?
It does make sense. And just from my side, a couple of things. I find in these exercises, and again, I haven't worked with map byte buffers in ever, essentially. But what I find interesting is, when you have a way to read in a file, it's such a great exercise, even for your projects. Just, use the 4 or 5 different APIs to, read in a file. Just compare these numbers and get experience with all of these things. Don't just be stuck with using, one set old method and just keep going with it. Finding real hard numbers and a real baseline is a super nice thing to do. And I think it goes with every of these. Integration is a big word, but let's say reading a file, shoot an SQL query. If you just work, for example, in Java, and then you have an ORM, and then you let you auto-generate 20,000 SQL queries. Just take one SQL query, open up the command line, log into your Postgres or SQL Server, whatever have you, execute the query, and see what the speed actually is and how you can improve that speed, and rearrange the query then in that way. And just playing with these tiny what I would call them isolated, blah files, is just gives you a huge learning effect.
I would also underscore one little thing about what you said there, just also because we haven't really, this isn't a full performance course, right? So we haven't maybe talked about some of the preliminaries, but one thing that's important to distinguish too is latency versus throughput. These are two very different things. Like you were talking about the MySQL queries, or not MySQL queries, but SQL queries. Maybe you're probably not using MySQL, but let's.
I actually also partially am for my own projects. But yeah.
Okay. Either way, you're using some database.
Yeah.
One thing that you also run into, and we'll try to be cognizant of that here, because we may encounter a little bit of this as we go, is sometimes systems can process more things if they're done sort of in bulk than if they're done one at a time. So one of the much harder things about, for example, the SQL query case that you said, is it's hard to optimize a single SQL query because you don't know what will happen if you give lots of SQL queries. Databases are often optimized for the total amount of queries they can handle per second, not how fast they handle one individual query, right? They don't often optimize for the speed at which they can give one back, which means that if you push a bunch in, you might get them back in less time than if you just took one and multiplied it by the number you're going to do. And this might affect how you optimize as well, because it could be that certain structures of queries are better for this pipelining than others, right? In this particular case, we haven't quite gotten to a place where we need to think about that yet. We might, but we haven't yet. So here we're just wondering what's the speed of how fast this come off the drive. We're not really thinking about overlapping yet. So in this case, we don't have to worry about those two things.
Right.
So there you go.
And to cut a long story short, for you, the viewer, play with these file APIs. It's a great exercise. We now figured out, using file channels is pretty fast. We're going to go forward with that. And that is where we actually, I think we could already come to the homework section.
Okay, great.
Because I was thinking, let's just make we now know how to read in a file. Yeah. Yes. Let's just make the program, I will propose, let's just make the program work. Then we can optimize it later. And along the way, we could look at all the JVM internals. We kind of look at, we're going to have a look at how the async debugger works, what we can profile with it. And is that the way to go forward? Would you recommend that?
Yeah, that sounds great. And one other thing that I would like, if you could, is, are you streaming from a separate machine, or are you streaming from the same machine you're running benchmarks on?
It is the same machine, unfortunately.
Okay, so one thing that you also have to be aware of as we go forward on this is that will affect your performance quite a bit. It might not necessarily affect the disk performance because your streaming might not really be stressing the disk I/O subsystem, but the processor and things like that will be getting hit. And so, optimally, if you want, maybe if this series is looking promising, maybe your employer will send you a separate machine, and you could do capture on that and stream, because it's very important for performance to make sure we know what we're working with. But if not, we're going to have to be cognizant as we move forward, because once we move off of disk I/O, we're going to get into the realm where the streaming itself will affect it, and you'll probably have to take some timings with and without streaming just for us to figure out how much it's burdening CPU.
And I could even just use my laptop, I guess. In terms of, but we'll I get.
I'm trying to get you a free machine here, Marco.
Free machine, right?
What are you doing? You can't use your laptop.
Okay, well, my work laptop. Well, I'm going to figure something out. Right?
Okay.
But just, let's say homework. We're just going to put it bluntly. Get the thing to work. It doesn't matter what the speed is. And then we're gonna dig a bit deeper into the first. How to understand where we lose the speed in the next episode. Dig a bit deeper.
I'd add one more thing to your homework, if you don't mind.
Yeah.
Can you get us working off of a RAM drive as well? Because we will want to kind of play with this challenge at some point, and since now is the time when you're working on disk I/O, let's try to get it so we can run both ways. Right. Once with a RAM drive, once without. Now, this RAM drive won't be exactly the same as the Hester one, but then again, our SSD wasn't going to be either, so no real difference there. We're still going to be having to sort of account for the difference between the two machines when we ballpark how we're doing, but yeah.
Okay, cool, yeah, we'll do. And I'm just going to put a note down for, the profiling section, whatever, we'll have to see. There's tons of stuff about Java profiling I would love to get into. Let's see when we can do that. But I'm going to just come up with a very simple, stupid version. If it bloats up the baseline again to 50 seconds, so be it. Then we have to dig deeper again into how to get from 50 seconds back down to the 2 seconds or whatever it is.
That's why we're here.
Awesome. Then that is already the end of this episode. We set the baseline, I/O baseline. Thank you very much, Casey, as always. And
my pleasure.
See you again next time.
Yes, thanks for having me. Have a good one, Marco.
You too. Bye-bye.